Welcome back. My name is Renee Clary, and in this video lecture we will take a look at metamorphic rocks and the processes of metamorphism. Metamorphic rocks are one of the three main types of rocks and as such are very involved in the rock cycle. And as you might imagine, metamorphic rocks are very closely associated with different plate boundaries. We do find metamorphic rocks at all three plate boundaries, but regional metamorphism, or the metamorphism that takes place over a very large area, is associated mostly with convergent plate boundaries. Let's get started. Metamorphism, by definition, is the solid state transformation of pre-existing rock due to changes in the physical environment. Now, what this boils down to is that we need to keep in mind the changes are in the solid state. We cannot melt, because if we do melt the rock, we end up with magma, and when that cools, we'll have an igneous rock. There are three recognized agents of metamorphism. These include heat, pressure, and chemically active fluids. If we try to relate metamorphic rocks with the two other rock types, primarily the sedimentary rocks and the igneous rocks, we will see that metamorphic rocks form somewhere between the two limits. So sedimentary rocks are mostly formed near the surface of the earth, and the temperature and pressure conditions are not as steep as those of metamorphism. Igneous rocks form when molten lava or magma crystallizes, and as a result, igneous rocks require higher temperatures and pressure, or lower pressures of formation. So the limits of metamorphism would be from about 200 degrees Celsius all the way to melting. We don't want to completely melt the parent rock, because if we do, we end up with magma or lava, and when that cools, we don't get a metamorphic rock. We get an igneous rock. We're also looking at pretty high pressures as well, about 300,000 atmospheres, greater than about 300 megapascals for metamorphism. Again, this is between sedimentary and igneous rock parameters. There are many different parameters for metamorphism. We'll look at that a little bit in more detail later on in this lecture. Metamorphic rocks, of course, can form from any existing rock, sedimentary, igneous, or another metamorphic rock. What do we mean by fluids? Well, fluids can be liquids, such as water, or gases, such as carbon dioxide. A typical fluid involved in metamorphism consists of water and carbon dioxide and some dissolved minerals. It's important to have this active fluid because the fluid can supply hydroxyl for metamorphic reactions. It is a source of the hydroxide ion. It can also prevent some reactions from occurring. So if fluids are present, some metamorphic reactions or some chemical transfer reactions will not occur. And finally, if the fluid leaves the area of metamorphism, that action can actually preserve the metamorphism that has taken place. Let's take a look at pressure. Pressure at depths deep inside the earth is what we call confining pressure. This is essentially equal pressure in all directions. If we want to talk about the pressure that results from an overburden of rocks, we're talking about lithostatic pressure. Hydrostatic pressure, on the other hand, would be a confining pressure that would result from water. For example, if you were a scuba diver and you are in your apparatus and are deep in the ocean, you will feel pressure in all directions. This is confining pressure. The deeper you go, or the more water over you, and in the case of rocks, the more rock over you, the more pressure you will feel. For example, look at that volume of the box From the surface, when you are at the surface, we have normal atmospheric temperature and pressure, but as something is buried, it's subjected to more pressure. Bring it down below the surface even farther and look at the additional pressure and changes in volume that can result. One of the greatest representations of this, I think, is with this styrofoam cup. This is a typical styrofoam cup that you would put coffee in the morning. Now, when a cup like this was subjected to 750 meters of water below the Antarctic ice sheet, this is what resulted in the middle. Bring it down even farther below the surface, 1,500 meters, and look at the change in volume. It's crushed. Pressure does not have to be confining. It can also be differential, and that means that it acts unequally on different sides of the rock. The rock ends up being distorted because the pressure is not the same in all directions. We can have directional compression that results in flattening, and we can also have shearing. Shearing involves the force with parallel but opposite movement. For example, in the top representation we have a hand holding a dough ball, and if you squeeze that, you have compressional flattening. However, put two hands together with the dough and slide one forward and one backward, and you end up with shear. How does this relate to rocks? If you have differential pressure or higher pressure in one direction, you can result in flattening in that direction. Here we have on the left hand side, we have a picture of a granite, and if that granite is subjected to high pressure, especially pressure that is in the right hand photo, if it's coming from the right hand direction, we have higher pressure there. Look at the flattening of the mineral pattern. The elongate minerals line up parallel. They're better able to counteract the pressure that way. There are three main types of metamorphism: contact, dynamic, and regional. And we'll take a look at each of these today. Let's start with contact. Contact metamorphism occurs at or near the contact of igneous rock. In other words, that hot magma is coming up through country rock, and it essentially is baking the rocks that it is intruding into. The agents of metamorphism with contact metamorphism would be heat, primarily, and fluids, chemically active fluids. The resulting area of metamorphism is called an areole, and as you might suspect, the intensity of metamorphism will decrease as you move farther and farther away from the contact of that igneous intrusion. Here is a diagram showing a granite pluton in the middle corner at the bottom of the diagram. And as that magma was first emplaced, the country rocks were affected. They were metamorphosed. Notice the area of metamorphism. As we move immediately beyond the granite, we have a hornfels zone. And then we move farther away and the metamorphism was less. We have an intermediate zone with some biotite. We move farther away from the contact. There's a zone with some spotted shales, and finally we get to an area of unmetamorphosed rock, which is the original country rock. This is a great photograph. It shows the contact zone between a hot intrusive and the existing country rock. You can see how the metamorphism decreases. There are different layers of metamorphism as you move away from that intrusion. Metasomatism occurs in contact metamorphism, but it's different from contact metamorphism. In contact metamorphism, we aren't really affecting the chemistry of what is existing in the country rock. We're changing with heat and active fluids, but in metasomatism, the fluids that are moving through the veins and dikes dissolve some of the rock constituents in the country rock and precipitate other constituents that have been dissolved and carried out of the magma. And as a result, we can get some valuable ore deposits. For example, copper, iron, lead, tin, and tungsten, and zinc have all resulted from contact metamorphism and metasomatism. In this diagram, we see that the tungstate ion is moving out of the magma, and it comes in contact with the existing country rock, which in this case happens to be limestone. So the tungstate is going to replace the carbonate ions in calcite. The resultant ore is mined for tungsten. Tungsten is used for a variety of industrial purposes, including it forms the filaments in incandescent light bulbs. Dynamic metamorphism is the opposite end of the spectrum, if you will. Metamorphism that occurs along a fault involves high pressure, but not very high temperature. This would be dynamic metamorphism. So the agent of metamorphism, the primary agent, would be pressure. We have differential pressure in this case along the fault, and shear pressure, because usually we have faults moving in parallel but opposite conditions, and this would be the case of a lateral fault, for example. The resulting rocks are termed mylonites. There is an artist's representation actually of a mylonite showing how there has been shear and movement along the direction. In this case, we're probably looking at direction that is in a northwest to southeast direction. Here is mylonite exposed in the Adirondack Highlands in New York. But by far, the most common type of metamorphism is termed regional metamorphism. The agents here are high pressures and high temperatures. It's most common in convergent plate margins where there is a subducting plate, but it can also occur in divergent margins at a shallower depth. Regional metamorphism affects country rock in large areas and to great depths beneath the surface of the earth. There is a gradation in metamorphism, and we can recognize this gradation by the minerals that are present. So if we look at old mountain belts, we can see areas where metamorphism was very common, and likely metamorphic rocks are found today. In this map diagram, you see that there are shields, and the shields are kind of that purplish color, and this is the old basement rock that forms the core of a continent. And then you see all the little upside down V's, if you will, that show some of the ancient mountain chains. And where those mountain chains are located, chances are you will find a great variety of metamorphic rocks. So, we can look at the degree of metamorphism and see the type of pressure and heat, low to high, based on different zones or grades. A zone is the first appearance of a new metamorphic mineral. This is based on a classic study done by Barrow in the Highlands of Scotland. And what Barrow found were index minerals located with varying degrees of metamorphism. For example, with little heat and pressure, chlorite was formed. As we increase the degree of metamorphism, biotite would show up, then garnet, staurolite, kyanite, and sillimanite. So if rocks had chlorite, they weren't as metamorphosed. If they had sillimanite or kyanite, this would indicate a greater degree of metamorphism. So if we look at increasing metamorphic grade again, we're starting at chlorite with very low metamorphic conditions, and then we move to intermediate conditions, and biotite and garnet start to show up. And then as we get to extreme heat and pressure, we see staurolite, kyanite, and sillimanite. This diagram will show you the rocks. We're looking at clay rocks and the varying types of minerals. We see chlorite, muscovite, biotite, garnet, staurolite, kyanite, and sillimanite. We're moving from lower metamorphic conditions with the chlorite to high metamorphic conditions with the kyanite and sillimanite. Well, not only do we see that pattern in Scotland with Barrow's classic study, but here we see an area in Wisconsin that has been metamorphosed. Notice that the green represents the younger non-metamorphosed rocks, and then we see chlorite in kind of that yellowish color, and then biotite, garnet. We're moving into the browns with staurolite, and the very dark brown with sillimanite. Now, which area do you think was subjected to the highest temperatures and pressures and the greatest metamorphism? Right there. Because sillimanite, staurolite indicate a higher degree of metamorphism. There's another way to look at varying degrees of metamorphism by the rocks that are present, and we can look at facies as opposed to zones. A metamorphic facies is a group of metamorphic rocks that are characterized by a particular mineral assemblage. We're not just basing this on one rock. We can have a green schist facies that is indicative of high temperature and, of low temperature and low pressure. And amphibolite facies, we're slowly moving up with the temperature and the pressure. The granulite facies, we're still increasing with higher temperature and pressure. And with a blue schist facies, such as at the top of a subduction zone, we have low temperature but very high pressure. Now, green schist facies are commonly characterized by the mineral chlorite, and I brought a sample to show you. Chlorite is a green rock, and again, it's indicative of low temperature and low pressure metamorphism. Now, if we move up in temperature and pressure, we can get amphibolite facies, and here is an example of amphibolite. Even higher temperatures and pressures would give us a granulite, but low temperatures and high pressures would result in a blue schist facies. We can diagram that as well. And here you go. Note on this diagram we have pressure on the y-axis and temperature on the x-axis. If we increase the pressure but keep the temperature low, note that we get that blue schist facies. If we increase the temperature and the pressure, we get eclogite. We can have granulite with very high temperature and increasing pressure. Note that the green schist, which is just to the left of that blue schist facies, involves pretty low temperatures and pretty low pressures. Okay, so how can we relate metamorphic activity to plate boundaries? Well, if we look at divergent plate boundaries, we tend to get low to medium grade metamorphism. We may have a little bit of regional metamorphism, but it tends to be at pretty shallow depths. Transform plate boundaries, as you might suspect, would have dynamic metamorphism. Again, this is the agent of metamorphism in this case is high pressure, but not necessarily high temperatures. Oceanic continental convergent boundaries we end up seeing what are known as paired metamorphic belts. We have regional metamorphism to a great extent geographically and to a great depth. Paired metamorphic belts involve dynamic metamorphism in the accretionary wedge and the forearc basin of the subduction zone, as well as regional and contact metamorphism within the arc itself, within the continental volcanic arc. So we have, again, dynamic metamorphism in the wedge and the forearc basin, and we have regional and contact metamorphism within that volcanic continental arc. So here we have the accretionary wedge in the forearc basin. Primary agent of metamorphism here would be pressure. And the pair, the other end of that paired metamorphic belt, would be here in the arc. We would be looking at regional metamorphism as well as contact metamorphism. So we're looking at heat and pressure, and also we're looking at chemically active fluids, especially with that rising magma in contact. Note the different facies on this diagram. We have the blue schist facies symbolized by BS. I just circled that in blue. That is a low temperature but high pressure metamorphic facies. We can have a green schist facies outlined in green. Green schist facies occur when we have low pressure and low temperature. If we increase temperature and pressure, we can end up with the amphibolite facies. That's symbolized by A. And of course we can move further down in that zone and get to a granulite facies, which results from even higher temperature and pressure constraints. Okay, so how do we classify metamorphic rocks? As in any other rock type, we go back to texture and composition. Now, in metamorphic rocks, some of them exhibit a very special texture caused by metamorphism, and this is known as foliation. So we commonly divide metamorphic rocks into foliated and non-foliated rocks. Let's look first at the foliated rocks. In foliation, the minerals are arranged in a parallel and layered fashion. These are elongated minerals, and they tend to line up in a parallel layered fashion. We can use a mineral or a rock modifier to indicate the composition. What do I mean by parallel layered fashion? I'm going to show you in just a minute. Here we go. We have elongated minerals before metamorphism, and if we add stress, differential stress in this case, we're looking from either side. Note that those platy elongated minerals will line up and we'll see a banded rock. So before we have individual crystals, different minerals, and after the pressure, after metamorphism, we end up with these bands, these layers of minerals with their platy sides aligned in a nice parallel fashion. Up close and personal, here is a granite, and there is the resultant gneiss. Let's do that again. Granite, look at the crystals, and now after pressure, gneiss. This is what foliation looks like under the microscope. You can see the different minerals, again, are lined up in a nice parallel fashion. If we look at clay rocks, we have increasing metamorphic grade from slate all the way to gneiss. We're also looking at increasing grain size as we move from the left of that diagram all the way up to the right-hand side with the high-grade metamorphism gneiss. So we have slate, phyllite, schist, and gneiss. Slate occurs at the lowest temperature and pressure constraints, and then as we move up we get high-grade metamorphism in gneiss. You can't see the individual crystals without a microscope with either slate or phyllite. In schist, the foliation is apparent, and in gneiss, the rock is banded as lenses or layers of the minerals accumulate with increased foliation. This is slate, and I brought a sample here to show you. This is a red slate. Commonly we'll see it in this nice gray color. Notice the different layers here. This is known as slaty cleavage. Okay, I have a picture of this in situ in a rock outcrop. There we go. Slaty cleavage results from finely laminated foliation. This allows the slate to split easily into thin sheets. So what you see in this photograph is an exposure along a riverbed near Lexington, Virginia, and you can see those different layers, or the slaty cleavage. This has made slate a very valuable building material. This is a slate roof on a chalet in Switzerland. We can look at the slate again up close and personal. It has roofed many houses and buildings. If we increase the degree of metamorphism, we end up with a phyllite, and I did bring a sample to show you that as well. Okay, this is a phyllite. Let me bring the slate back, the red slate, and you'll see the differences here. We've increased the metamorphism grade with this guy. A lot of times you'll see phyllite samples that look a little wavy. They almost look like gunmetal. Okay. And then, moving up in the metamorphic grade, we move to a schist. Schistosity, or schistose foliation, produces a wavy surface when the rocks are split. So this can be really problematic with mass wasting and landslides. The high mica content will make the schist reflective. You can see that wavy foliation in this photograph. And there is a photograph of a garnet mica schist. We can use, again, a rock modifier or a mineral modifier to more accurately describe the rock. Those individual garnets are pyphoroblasts. They're larger crystals that nucleate and grow, and they tend to either incorporate some of the layers or they actually kind of push them aside as they grow. I've also brought a little hand sample of a schist. This is not a garnet mica schist. There are no garnets here. It is a mica schist. Note how highly reflective that is. And you can see the individual layers here. Pretty easy to determine. And you can also see some individual crystals. You can't see that in slate and phyllite, but the foliation does become very, very apparent in a schist. Now, if we move up to the highest grade of metamorphism, we end up with a gneiss. With gneiss metamorphic rocks, you can observe banding. So you see those layers of minerals. This is a garnet biotite gneiss. You can see the garnet crystals. The biotite is the black mineral. And I brought a hand sample as well. This is a biotite gneiss. Again, you can see the layers of the different minerals. They have aligned. They are now parallel. I have a photograph of gneiss in an outcrop. And there we go. Look at that folded gneiss. Great texture, and that is located in Ontario, Canada. Other foliated metamorphic rocks include amphibolite. It's a dark rock made from hornblende and plagioclase, and I have that as well to show you. I have a hand sample. There's an amphibolite. plagioclase, and hornblende. Okay. We also have other types of foliated metamorphic rocks, including stretched pebble metaconglomerates and migmatites. Migmatites have both igneous and high-grade metamorphic characteristics. We try to file rocks that are formed on the earth in nice, neat categories: igneous, sedimentary, and metamorphic. But as you might imagine, there becomes a fine line that some geologists draw and other geologists draw differently between igneous and metamorphic rocks. So migmatites appear to have high-grade metamorphic characteristics, and there may be partial melting, though geologists don't always agree on the melting. Here is a photograph of a stretched pebble conglomerate. This is in Southwest Virginia. And check out the migmatite. This is in the San Gabriel Mountains in California. That, of course, is along a subduction zone, so there was high temperature and very high pressure along that western edge of our continent. We have non-foliated metamorphic rocks, so we can't really rely on that foliated texture. Instead, we're looking at mosaics of equidimensional minerals. They do not contain platy or elongated minerals, so what we do tend to see are larger crystals or larger grain sizes that result from recrystallization. Our non-foliated metamorphic rocks can be of one mineral type. For example, quartzite is formed from from quartz. And we can also have a marble that is metamorphosed limestone, or we can have non-foliated metamorphic rocks that have very small crystals. So they may have different minerals, but the crystals are very, very tiny. We have to rely on the composition. So again, if we're looking at calcium carbonate, limestone, if that is metamorphosed, we end up with marble. And I have a piece of marble to show you here today. Marble comes in very many different colors and has some nice veining at times. Very nice size crystals. I don't know if you can see that from this angle, but nice larger crystals. Okay, we can also have a metamorphic rock that results from the metamorphism of silicon dioxide or quartz, and we end up with a quartzite. And I have a hand sample to show you of quartzite. Again, different colors of quartzite as well. But what happens when we don't know that the composition is uniform throughout the rock? We can end up with a greenstone, which is a compact, dark green, altered mafic igneous rock. We can also end up with a hornfels, which is a fine grain rock, and it results from contact metamorphism. And I actually have a hornfels to show you. There we go. Again, it's fine grain, can't see the individual crystals, and this results from contact metamorphism, a hornfels. Okay. And we can also have anthracite. Anthracite is known as hard coal. This is the metamorphic version of bituminous coal. Limestone, again, metamorphoses to marble, non-foliated. Quartz sandstone metamorphoses to quartzite. And these are non-foliated metamorphic rocks. What is the economic value of metamorphic rocks? Well, marble is used in building materials as well as sculpture. Slate is used for roofs. It was the basis of our blackboards in schools for many, many years. Whiteboards have now replaced that. Green schist is also used as a building material in some areas, and metamorphic minerals have value as well, such as garnet, which is January's birthstone in gemstone quality, but garnet can also be used as an abrasive and a polishing agent. Talc, used as an additive in many things, including powders. Kyanite and asbestos. Asbestos is used, of course, as an insulating material. Well, that will conclude our presentation today on metamorphism and metamorphic rocks. It is meant only as an overview, so if you have any questions or need further clarification, please feel free to post your questions on the discussion board or email your instructor. Thank you so much for joining me today, and have a nice day.